Our speaker, Akwasi Boateng, is the lead scientist of the Thermochemical Biomass Conversion Program at the Agricultural Research Service, or ARS. This is the principal research arm of the USDA. He is located at the USDA's Eastern Regional Research Center in Windmore, Pennsylvania, and functions within the Sustainable Biofuels and Co-Products Research Unit. He leads the research on catalytic and non-catalytic pyrolysis for the production of fungible transportation fuels from agricultural residues and energy crops. Dr. Boateng is also the co-leader of the ARS Biochar initiative. Both of these research activities are national priority efforts in the agency's critical mission of meeting America's fuel independence and solving global environmental sustainability issues. Prior to joining ARS in 2003, Dr. Boateng held engineering faculty positions at 2 universities and worked extensively in the mineral and materials processing industry. He received his PhD from the University of British Columbia. He's a fellow of the American Society of Mechanical Engineers and a senior member of the American Institute of Chemical Engineers. He has authored about 90 publications, over 70 of which are peer-reviewed. In the last 5 years, he has secured positions as the principal investigator, or co-PI, on 8 grants that have provided over $10 million in total funds to his research program and over $90 million in overall funding to team projects nationwide. His webinar today will present a collection of knowledge developed during research into sustainable biofuels and co-products at the ARS over the last decade, addressing thermochemical conversion of biomass to fuels and chemicals via the pyrolysis platform. This presentation will cover the basic principles of the platform, thermal-only pyrolysis, and instability issues in the product distribution. We'll also see a few technological developments that help deal with these issues, including reactive pyrolysis, catalytic pyrolysis, as well as feedstock selection. So at this point, I would like to turn it over.
Okay, the title of my presentation is a pyrolysis of biomass for fuels and chemicals at the U.S. Department of Agriculture. And I will talk about, I think I want to give you an overview of the pyrolysis and national biofuels agenda. And then tell you a little bit about the technologies we've developed here, including thermal-only pyrolysis and pyrolysis upgrading. And then I'll show you some of our best results to date, and then tell you about a project which resulted from the results I will be presenting. So I'll start with this slide number 3 here, which I'm sure you're all familiar with it, which is the US EPA Renewable Fuel Standards of 2007, the mandates. And if you see on the left, the graphs there shows how we're going to replace by 2022 about 36 billion gallons of fossil fuels in the United States with the renewables. And I would rather backtrack a little bit to sometime, if you all know, about 1980. At that time, much of the U.S. biofuels research effort had been devoted to corn ethanol, and but by 2004, sometime there, if you recall, the food versus fuel argument had spread a lot of interest in alternatives to corn ethanol, and that sometime around 2006, when President George Bush touted the potential use of switchgrass for cellulosic ethanol in his State of Union address. So by 2007, about when the RFS2 was established as part of the ISA, the National Action Plan essentially read ethanol only, and that the U.S. was to meet the new renewable fuel standards solely with cellulosic ethanol. It was soon realized that even with cellulosic ethanol, the mandate set by the RFS2 would not be forthcoming. And if you recall recently, that this had to be revised substantially. Some of the challenges included, among others, various recombinants that are needed for pre-treatment of various biomass resources. You all know about the recalcitrance of lignin, and importantly, the large economies of scale associated with the biological processes. And also, the U.S. ethanol blend wall, as you know, is set at about 10% of gasoline for the foreseeable future. And that gives a limited room in the market space for both the grain and the cellulosic ethanol. And therefore, the needs that we need to look at hydrocarbon biofuels. So at the time when the RFS 2007 time, that time thermal pyrolysis and the gasification had shown some promise to deliver transportation fuels, essentially because we had the experience of Sasol in South Africa, and also some of the proven processes in the catalytic upgrading. Some of the work by UOP and also at PNNL, DOE Labs, the Pacific Northwest. So 4 years later, in 2011, so far now the emphasis really has been shifted from ethanol to high energy density, infrastructure compatible biofuels, which are typically hydrocarbons. So outside the United States, the governments of Canada, the EU, they were all supporting pyrolysis-based biomass conversion technologies and the research demonstrations. The focus in Europe, for instance, was developing the fast pyrolysis technologies for the production of bio-oil in high yields, and their emphasis has less focus on the deoxygenated infrastructure-ready hydrocarbons. Canada, for you all know, Ensign and other companies in Canada demonstrating mobile systems, some 1 ton per day for bio production from wood waste. In Germany, you know about the BioLeak process where they combine the bio oil and biochar slurry and gasify it and then produce dimethyl ether and gasoline from a syngas that comes out of this. Wood-based bio-oil production plants in Finland and Netherlands, normally some of these are focused on heat and power applications. So all these help and to really change the direction in the United States, and by somewhere close to 2008, the Biomass RD Board at that time redirected biofuels research funding towards hydrocarbons. That's after when some of these prominent people like the Secretary of Agriculture, the Energy, that time boardman, had given prominence to the utility of pyrolysis oil. So the first funding for pyrolysis actually in the United States, recent time was sometime around October 2008, and that was by DOE, which awarded about up to $7 million in funding to U.S. research organizations and institutions of higher learning. This funding was to serve to support the goals established in ISA 2007 for advanced biofuels, and also to support the DOE production targets. Don't forget another event that also made a change was that in 2007, ConocoPhillips had established a $22.5 million biofuels research program at Iowa State with Robert Brown to promote biorenewable fuels based on the biomass pyrolysis platform. And what is it, the pyrolysis that we're talking about? Essentially, pyrolysis is defined as the heating of organic materials in the absence of air. If you all know about the fire triangle, and to make fire you need you need a biomass, which is say your fuel source. You need heat, and then you need oxygen. And if you take out the oxygen, you are in a pyrolysis mode. And basically, most combustion is preceded by pyrolysis. It is when the volatiles are released and when air is set in, that's when you see the visible flame, that's the fire that associated with the combustion. So pyrolysis could be slow pyrolysis or fast pyrolysis. The slow pyrolysis, you're all aware of it. That is when you dig the dirt, you put in your biomass, you set it to fire, you go home, you come back in 2 weeks, you dig it, you get big chunks of charcoal. That's a slow pyrolysis, which is slightly exothermic, so it can sustain itself. And you make more of charcoal. The pathway is towards carbon. But if you look at fast pyrolysis, you maximizes the liquid, and the heat rates are very, very high, about 1,000 degrees per second in some cases. And what you get are 3 product streams as a bio oil, as something that you see here, like this, which is oil that resembles a crude oil, but it's not. And you get small amount of biochar, about 20% or even less, depending on the biomass, and the syngas that you can use to run the process. So that comes with a very high heating rate and cooling rates, and the temperatures that you maximize the liquid will be around somewhere 450 to 500 degrees C. But the liquids are complex mixtures of oxygenated hydrocarbons, and it includes a lot of water. So these are, because they're oxygenated, you have a lot of acids, esters, ketones, aldehydes, sugars, and a lot of oxygenated compounds. The heating value can be somewhere between 20 to 30 megajoule per kilogram, depending on the biomass, and that will put you somewhere around 50 to 75% of that of heating value of petroleum fuels. It's acidic. The pH is around 2, and therefore it's very unstable. And over time, condensation reactions and molecular weight increases take place, molecular weight increases, viscosity increases, you make more water. Essentially the same as similar to the biomass in terms of oxygen content. It's deficient in hydrogen compared with petroleum. But you can make a lot of it. The yields can be as much as about 60 to 70% in liquid yield. So it's very high if you can find uses for it. The cost of producing a barrel of it is reported to be somewhere around from $30 all the way to $50. And P&L has reported that if you could refine all this in an existing infrastructure using the 16 hydrogen infrastructure, then the gasoline selling price could be somewhere around $2 to $3 per gallon. So what was our role at the USDA? The funding shift that I talked about in the first funding that DOE provided for pyrolysis was therefore to find a way to stabilize the pyrolysis oil that I just showed you. And if we could stabilize it, reduce the oxygen content, and then we can have some immediate uses as you think about how we can upgrade this to transportation or infrastructure ready fuels. So that $7 million went to about the 4 awards were made, and that included the UOP consortium that we were part of. That same consortium included P&L, Ensign, who's a company in Canada, NREL, and Power Corporation. Our role was to use, if you can use some of the UOP catalyst, heterogeneous catalyst, zeolite catalyst, to replace the sand bed and the fluidized bed, and then crack some of these vapors in it so we can reduce the oxygen at the incipient pyrolysis process. University of Massachusetts, George Huber's group also was working on similar things, catalytic fast pyrolysis. Following this award, a year or two after, there was also a big one that came from the ARA. That's the American Recovery and Reinvention Act. That was about $35 million that was led by DOE and PNNL. This also included the UOP group, which included ARS. At the same time, ARS was working with Siemens on automation and controls and building reactors at the ERC. That's where I'm located at USDA. So in the next slide, I show that here we used, for the part of the project, we were to use ARS fluidized bed technology system you see here, that we call here the Quasinator, to really screen some of the UOP catalysts. So the Quasinator is essentially the fluidized bed of sand, as you see here, and we feed the biomass in it here, and the sand bed is heated and it's agitated and it's fluidized, and the biomass is decomposed completely in here, and then it's carried up here and dedusted. The char is dedusted here, and we got to stop the reaction quickly to quench it with these four condensers, we call them pinches, to remove, to condense the vapors into liquid. What is not condensed comes to electrostatic precipitator, which is ESP here, which we collect most of our liquids. Essentially, this is designed to process 5 kilogram an hour biomass. We operate somewhere around 2.5 to 3 to 4 kilogram an hour, depending on the biomass. So the work we did at UOP, we replaced the sand bed with a UOP catalyst and do the same thing and see if we can reduce the oxygen content and stabilize the pyrolysis oil. By the end of the project life, the 3 years, ARS had developed a catalytic fast pyrolysis process for the production of pyrolysis oils from several agriculturally relevant feedstocks with reduced oxygen content. All the publications are listed here if you are interested in. So what do you do with a catalytic fast pyrolysis? Essentially, if you replace the sand bed with a catalyst, we call it in situ catalysis. And you can also put the catalyst outside the condensers, so you can then crack the vapors. You call ex situ pyrolysis. So these catalytic processes often result in the production of deoxygenated pyrolysis oils. The oils are typically, since the biomass is hydrogen deficient, you produce aromatics based on the chemistries you see down here below. So this will show you some of the data from the UOP work that we did. As you see here on your left hand side here, you can see the yields of the normal thermal only pyrolysis around 62% in this case for oak. When you use a UOP catalyst, the yields are reduced to as much as half or even less than half. The elemental analysis is here. This is a carbon is sometimes improved on the last column here with the weight percent of carbon increasing from about 52% to 76%. Importantly, the oxygen content reduced from about 41% to as low as 17% with certain catalysts. The heating value therefore shoots up from 22% to about 32%, which is a very good deal. Product distribution wise, you see that the bioactives of the acetic acid or the carboxylic acids are reduced. In this case, acetic acid comes from about 10 to about 4.5%. But importantly, you see the youth start to get in some of these hydrocarbon molecules, which were only traces in a thermal-only pyrolysis. But the one thing I need to mention is catalyst use does not achieve the desired results without catalyst regeneration. So it's important that you design a system such that you can regenerate a catalyst. If you leave it in there within less than 5 minutes, already catalyst is poisoned. So that's why UOP was very interested in this, because it's amenable to FCC type technology, which is continuous regeneration of catalyst, which they invented. The ex situ catalysis is external. We use put a catalyst in an external reactor separate from the pyrolysis reactor, and that's basically vapor cracking. So you do you remove the you generate, do the pyrolysis over sand, and if you put a catalyst bed after the condensers, what you have this is a progressive removal of water vapor, light oxygenates, and solids from the pyrolytic vapor stream. So you do that, and then you follow in the catalyst bed, the protonation, dehydration, isomerization, and cyclization, and then you aromatize into aromatics, as you see here. So with the NABC work that followed the Pi stabilization project, ARS investigated here, we worked on expanding the catalysts that we screened previously from UOP to include several ones that came from Albemarle Corporation of the Netherlands. That NABC project is called the National Advanced Biofuel Consortium. It was a 3-year project, but after the first year, they were to down select some of the technologies to move forward. And after 1 year go no go, UOP pull out because they thought they had sufficient knowledge to venture into commercialization of the process for the production of hydrocarbon fuels. And they form a joint venture with the ensign called Envergent, that you all might be aware of. They are the one that is building the demonstration unit in Hawaii based on this process. So the ARS will show that pyrolysis oil produced over UOP, some of them proprietary beta type zeolite catalyst in situ, that is when you replace the sand bed and fluidized bed with a catalyst, contain as low as 15 to 20 weight% oxygen. That ARS moved on after UOP moved out, and we went on to develop our own portfolio of technologies, pyrolysis processes, to include a whole slew of technologies for producing partially deoxygenated stable pyrolysis oils. Aside from the catalytic pyrolysis I just described, we developed what the patent pending non-catalytic pyrolysis process involving a reactive gas atmosphere that we call TGRP. We also developed technologies in the presence pyrolysis technologies that work on the co-reactants in addition to cellulosic biomass. And the co-reactants could be any feedstock that really inherently go to low oxygen content, and these include some of the proteins, lipids, and plant resins, and also adding agricultural plastics into some of the cellulosic material that we pyrolyze. In this slide, I'll talk about a tail gas reactive pyrolysis, a TGRP, that I just mentioned. And this does not involve catalyst, but it involves returning some of the tail gases conditions to a point where we significantly reduce the oxygen content to less than 10%. And this was reported in AG Ag Professional. That's a news letter, and also ARS magazine. And essentially what it does is it returns some of the gases here, and the atmosphere could be enriched in CO, CO2, hydrogen, and some light hydrocarbons. But we have a sweet spot that we operate at where others cannot achieve the same way that we do. So if you look at the next slide in here, with this TGRP process, we can essentially look at product distribution. We can reduce, if you use catalytic pyrolysis, acetic acid is around 4.5. In our sweet spot, we can get as low as half of that. But importantly, we can get some of these hydrocarbon molecules. They are all enriched in our TGRP process. This work is published in Energy and Fuels, and if you're interested, you can follow that. Most importantly, this process allows us to produce an oil which is highly stable, and thermally stable, that we can distill this or hydrogenate using just on the shelf type of catalyst. This slide shows you how we can just not even doing any upgrading, we can just distill that into variable products like a BTX, that's benzene, toluene, xylenes, and so on, and naphthalenes. So in this form. So imagine that you could do all this without the added cost of the catalyst, because it's very, very important step in our development. Also, you could opt to look for what type of biomass that can also inherently go to low oxygen or stabilize the pyrolysis oil. And what we find that the proteinaceous biomass can do just that. And chemically, it is just by the substitution of nitrogen for oxygen in the bio oil, which can be achieved due to the nucleophilic nature of the organonitrogen compounds, and that results from the catalytic breakdown of the protein in this type of biomass. So with that, I show you here, you can see some of this. If you look at corn stover, switchgrass, oak, if you compare that with some of the proteinaceous materials or feedstocks, you can see that, for instance, DDGS, for instance, you can get a carbon conversion up to around 74%, from 54 to 74. Camelina, the pennycress, and stuff, you get all this enriched oxygen content. It can be as low as even 6%, as some of them you see here, which is a really good deal. And for that, the energy content of these are simply just normal pyrolysis, no catalyst, can be very high. So for that, if you look at it, that means the oxygen content goes down as the protein content increases. And on this side here, it shows stability curves the bio-oils from the proteinaceous feedstock do not show rapid molecular weight increases with age. And this is a patent was awarded to ARS, USDA on this type of work. Now, whatever you do, you still have some oxygen in there. And if you really want to go to pure hydrocarbons as we envisioned, then you need to still do some upgrading work, and you have to then upgrade the condensed phase pyrolysis oil that you make. So generally, upgrading could take two forms, and that is cracking, that I've just mentioned, talked to you about, and hydrogenation, that where you have to remove the remaining oxygen or whatever oxygen in it using hydrogen. So normally this is a very high pressure systems, and then you can go to hydrocarbons. So typically what you do is, in this case, if you crack, you reject the oxygen through loss of carbon via CO2, and if you hydrogenation, what you do is you reject the oxygen as water. So several issues with this is due to high oxygen content of the starting material. It's not easy to really remove all of it without excessive use of hydrogen. And the leaders in this area will be PNNL and UOP, as I mentioned before. PNNL process includes about two-stage process over COMO catalyst, that's a cobalt molybdenum catalyst. The procedures that they develop, the UOP, are capable of removing the oxygen content to as low as a 10% dry weight with about 30% yield. However, the challenge is that petroleum-derived fuel feeds are typically less than 2% oxygen. Right. So if you have biomass, which is about 45% oxygen, you have to go all the way to 2% or less. And even the petroleum, the oxygenated compounds of petroleum, they are not this type of acids or something, they are alcohols. Initial studies at ARS which we conducted in upgrading were not very successful. And I show some of them on the right hand side here, and over on the shelf noble metal catalyst, palladium, ruthenium, and so on, and platinum. So we were able to look at the Kremlin diagrams here. Petroleum crude is somewhere here. We were able to move all the way somewhere here. Okay, though it's accepted, it's okay for this for combustion system, but it's not a crude oil. Work to date, in the conclusion, I can say that in order to capture the intended market of drop-in fuels and chemicals, it will require the following. You need to have an ensemble of technologies with pathways towards stable pyrolysis liquids in the first place. The process, either it's catalytic or non-catalytic, will have to combine with a certain feedstock selection in order to really to work well. It will have to be a scale, not where we're working at, but it will have to be a scale of somewhere around TR7. That's a demonstration scale. That's a technology readiness level of about 7. We believe it will have to be distributed on farm to decrease the collection radius. If it's catalytic fast pyrolysis, if it is required, then you need to address the catalyst robustness for on-farm use. But for non-catalytic pyrolysis processes like what we just develop a TGRP, you will need that in order to be economic, because that does not involve the catalyst cost, catalyst regeneration, and everything. The hydrogenation of the liquid that you make will need to address the appropriate selectivity to those distillate cuts that I presented. You need to worry about catalyst life and its stability and also its hydrophobicity, because whatever you do, the pyrolysis oil will have to contain some water in there. So therefore, with all this work done here, in 2012, September, we put all this together, and we were successful in getting a USDA and NIFA Birdie grant, and that would cost share brought we were awarded $6.8 million, and with a cost share about $8.6 million to put all these technologies together in an integrated form so we can operate on farm and demonstrate to address some of those these discussions or attributes that I just mentioned. So that grant that year, that was the last of the farm bill, the last farm bill, and that was about $25 million, and we were one of 4 recipients. And when the secretary announced that, he was at Renmatics right here in the King of Prussia area, and all he said that the goal there was just we were chasing the same molecules that we had before, and then he likened this with a Sheryl Crow's hit single that Soak Up the Sun, that said it is not what you want, but it is wanting what you have got. So you're looking at chasing after the same molecules, and all you need to do is expanding our radius to make it. So the distributed approach, I see, the concept here is the village scale. I'm sure you're all aware of it, that a lot of models have been done for this kind of approach. And the scale that people are talking about, including Google Inc., it's about 10 to 25 mile radius, scales about the 200 metric ton per day scale, that distributed on farm, and you move to a centralized place to process, either upgrade it for hydrocarbon or even produce electricity, like the Bioenergy process or something. But a lot of people have modeled this by various village scales, but nobody has successfully demonstrated its feasibility, its technical and economic feasibility, I must say. And even if the farmers can work together. Right? So there are still socioeconomic questions that need to be answered, and also the catalytics that you want to use, its lifetime, its selectivity, separations work. So that is what the money that we receive is going to do. And we do all that based on a logic model here. Some non-catalytic pyrolysis process, the low-hanging fruits will be electricity, and then catalytic pyrolysis with robust catalysts, and then we can produce and then upgrade into fuels and chemicals. So for that project, we selected 3 feedstocks: Swiss grass. Those 3 feedstocks are very important to agriculture: equine waste and woody biomass. And some of our partners in here, Mesa, Morrisville State College, University of Maine, you're part of this feedstock task. And then the multifunctional heterogeneous homogeneous catalyst, the University of Delaware, we're doing models. South Carolina, Rick Abuto's group, Maine, Oklahoma, Villanova, University of Sciences of Philadelphia. And then the sustainability issues, which should be part of Birdie, Drexel Sabrina's group with Swarthmore College. And then Sunny is helping Drexel. And then commercialization will be by Mesa and ARIA group near Reading, Pennsylvania. So our goal here is to build a large scale, take the quasinator from TRF5 and then bring it to TRF5, as you see here, and then bring it down here to on a skid mounted 2 ton per day process, which we will take from farm to farm. We'll station the farm for a certain amount of time and then move to the next farm. So we can then simply, instead of building 5 of them in different farms in a distributed manner, you will take 1 to each farm and you get the data that we need to then do the life cycle analysis on this distributed approach. The actual reactor technology is like you see here. It's like it got a twin fluidized bed, combustion and pyrolyzer. I call it combustion reduction integrated pyrolysis system CRIPS, and it's similar to FCC, except that is the design is slightly different, and we have a pattern which is we developed with the University of Pretoria in South Africa. The catalyst work here being led here, you see the chart here. University of Delaware will recommend catalyst using a computational catalysis, and then Villanova will provide supports. USC, South Carolina, will synthesize nanoparticles, and University of Maine will then do the test on model compounds, and ARS will then test on the actual pyrolysis oil. The assessment metrics, we are interested in Exergy analysis rather than energy, so that we can really capture the resource depletion and so some of that, working with the Swarthmore College on that. So the next slide here will be the farm bio PIs, which are all listed here, and we can go all of that, the names through here at various universities. You can see them for yourself. So a lot of people involved in this, including the companies and scientists, over students, graduate students, and ARS scientists. So too numerous to mention names, and this picture here will capture is a cross section of them as see here. And with that, I think I have finished my presentation. If you have any questions, I'll be happy to answer them.
Thank you so much. That gave us a great overview, and I especially appreciated the narrative of kind of where we've been and where we're headed in terms of pyrolysis in the U.S. Looks like we have one question already. Mike asks, which villages have you tried this with, and which places will your farm bio project be tested?
The farm bio project, I've always had the thing that I remember when I was in a meeting there. Cool Planet, what you call it, Carbon War Room. This question came out: where is the best place to do this village scale pyrolysis? People are talking about South America, Africa, and those places. And I tend to believe that if it's not proven in the United States, it won't work anywhere else. So we need to do it here first. And what we're working with the Pennsylvania farmers in the Delaware Valley here with the PA Farm Bureau. There are people who are growing switchgrass in our neighborhood, and they've been growing switchgrass looking for market for the past 5 years now. And we are going to work with them in the Delaware Valley area, in the Lehigh Valley. We also will take this to in forest, not only on farm, but also in forest in the main area. And when this is done, then we can look at going outside or abroad to look at actual villages, with people who may be interested. If Google it will be, then that's great.
For something like the Delaware Valley project, what would be your sort of estimated radius for actually traveling with the unit that would prove to be economical?
That's we find out. That's, like I said, it's all models. People say economical, it's actually not tested. So we want to select about 3 or 4 farms in around a 25-mile radius here, and then send these crips there, stationed there for a month each, and then so we can get the data and we can simulate distributed farm, and then we can tell you how economic that will be. But we will focus around 25-mile radius around here, and send the crips there, each of them, and factor in the distances in our calculations of the evaluation and stuff.
I see. We have a couple of questions asking about the timeline. Could you clarify what the timeline would be for actually getting the unit on the road for commercialization? And there's another question, if you could sort of identify some of the main constraints that you would see going forward.
The timeline is we are approaching the second year now. We are in our second year, approaching the end of second year. And this is a 3-year project. Hopefully we will get no cost extension for another year. We're hoping that the 3rd year, we are so far almost done. We're going to test this fire test by the end of the summer, and remove if we can fix all the bottlenecks. And so we hope by fall we will start to go to farm, and that will give us 1 year to really operate at the farm site. And then we will hope to get a year extension to evaluate our data. And after that, then we provide blueprints for commercialization. That's the first question. Second one was, if you could remind me, Sarah.
Identifying a few main constraints for the success of the project.
Yeah, the constraint will be the same barriers that we know of when farmers work together. That's the social sustainability issues that we talk about all the time. All right? And with the technologies and stuff really hold up on the farms. If you go for catalytic pyrolysis with a catalyst that we're developing vigorously with these partners, will they work actually on the farm? What are the yields? Will we really get a product that the refinery groups will just blend in seamlessly or not? How much will they be involved? Right? Those are the type of challenges, the barriers, technological and sociological, that we hope to address.
Do you have any kind of guess for, I'm assuming that if this is all happening on farm, there's going to be some kind of rental cost to the farmer to actually have the unit travel, either per ton or per hour of processing. Do you have any kind of estimate on what, so you had said that using existing infrastructure, which I guess this is a bit non-traditional, pyrolysis platform could provide $2 to $3 a gallon gasoline. Could you sort of estimate the portion of that would be taken up on the part of the farmer? Yeah.
No, if I had the answer, that would be end of the research. I don't have the answer. And what I want to see is perhaps we can at the farm get to low levels of oxygen that it will need only little processing at the existing infrastructure, where you go and ship the oil out completely. And then we envision that each unit will be at the farm, not that you take it there. All right? So that's the whole approach. this initial work is just because we don't have enough money to build 5 of them or 4 of them, something. But that's why we're taking mobile to go there. But again, I cannot predict at the end of this. Maybe the mobile type may be okay. Maybe the farmer will not want to keep this, right? We have some experience with how the combines work, right? And would a farmer want to own a combine, or they have a cooperative to own a combine, or so those kind of stuff? I don't know how the answer will be, and that would determine how much of the $3 or something that will be imposed on or come on the farming side.
Okay, thanks. There's another question that kind of gets at multiple use incentives for the farmer. There's a question asking, could pyrolysis be used for manure management and nutrient concentration for large farms?
Manure management, that's why we have in our portfolio of feedstock, we have horse manure. Right? And right now we are already collecting data as to how this will work compared with switchgrass that you cultivate and harvest. And so the Morrisville State College is leading this effort, and in the New York area they have a lot of horse stables and stuff, including even rehabilitation of horses and horse swimming pools and all those stuff. And we hope that this will be some opportunity fuel where it's already collected in one place, and therefore the economics will be completely different. So that I'm hopeful that will be part of the manure management and stuff that could be used for. That I can say. What was the second part of the question?
I think you addressed that question. He asked about management of manure and nutrient concentration for large farms.
Yeah. And the nutrient concentration is simply, I would say that the whole idea of the distributed thing is to remove the oil that you produce and leave the biochar behind, right? And that will be for soil amendment and stuff. And we've been successful in some areas in using that for pathogen removal, especially here at the ARS, using biochar.
Okay, thanks. I have just a clarification question. So for a given unit that's created, you mentioned the need to pair a catalyst with a specific feedstock. Would this be able to handle multiple feedstocks, or would it be really designated for a single feedstock that was most relevant to the farmer it was sold to?
No, if it's become one feedstock per catalyst, then we're going back to the same as same different recombinants for the biochemical processes for different biomass. The pyrolysis is a feedstock agnostic, and we hope to keep it there like that. In terms of processing, you don't need different ones, though different things in it may poison different catalysts, but that is not as severe as again, it's not only catalytic pyrolysis that we depend on. So, but pyrolysis is more forgiving in terms of feedstock, and you can use any feedstock. That's why we chose a wide array of feedstocks: switchgrass, herbaceous, woody, which is a woody biomass, and then manure. So all this, we have done this before, and they work. Just that we need to optimize that. So the feedstock here is different. It's not the same as biochemical processes.
Okay, thanks. It's about 2 o'clock, so if there are any last questions, go ahead and type them in. And if you want to stick around to hear the responses to those, great. In the meantime, I just want to thank Akwasi very much for the very great presentation. And would you mind typing your email into the chat pod, so in case anyone has any questions, or you could direct them to the ARS website maybe to take a closer look at some of your research?
I will do that just now.
Okay.
My email is okay. Email is right there. Let me okay. So you could click on this and I'll get it.
All right, thank you so much for speaking, and thanks everyone for joining us today. We'll be back next month, again on the second Tuesday, for the next in our series of webinars. Thanks a lot, Kwasi.